All right, in the second video on acids and bases, we're going to actually get into acid and base theory. So this can be fairly complicated. I personally think you could probably teach an entire semester class on acids and bases. So as you go through this, you may have questions. Please reach out and ask if you have questions, okay? The second thing is you may need to go back and look at something twice. That's okay, all right? If you need to rewind the video and watch it again, do so. But let's jump in. So we're going to talk about three things in this video. We're going to talk about the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory, and all of them describe acids and bases. We're going to start with the Arrhenius theory because the Arrhenius theory is the strictest theory. So that means it limits the number of acids to a very small number of acids compared to like the overall number of compounds in the universe. So what does the Arrhenius acid theory tell us? Well, number one, it says that acids have to produce hydronium ions in solution. So let's just unpack this because there's a tremendous amount of information here. Number one, it means water has to be present because we're saying in solution, and that implies that you're dissolving something in water. Second, we have to have hydronium. We have to have H3O+. And we're going to form that from the water that's in solution. And so our acid must be able to give up a hydrogen in order to be that acid. According to Arrhenius, our acids all taste sour. Okay, they will turn blue litmus paper to red, and they will react with the active metals to produce hydrogen gas. And when we talk about the active metals, we're talking about the metals in group 1 and group 2. Now, an Arrhenius base has to produce the hydroxide ion in solution. So let's break this down. Water has to be present, and OH minus has to be able to be formed. And so in the naming video, I said, hey, if you see a compound, a compound that ends in OH, assume it's a base. This is why. Arrhenius tells us if you have a hydroxide ion in solution, then you've got a base. According to him, our bases, okay, are going to taste bitter. They will turn red litmus paper over to blue, and they feel slippery. Now, when we say they feel slippery, bases themselves are not slippery. But when a base comes into contact with fat or oil on your skin, it will saponify. And saponification is the reaction between a base and fats or a base and oils, okay, whether they're on your skin or just, wherever. Saponification is a reaction that we use to form soap. So soap, saponification, that's where those two things come from. Now let's look at this in kind of a visual sense. So is HCl is HCl an Arrhenius acid? That's the question. Well, when we put HCl into solution, what happens? Well, the water, so let's see here. Switch over. So here's a water molecule. All right. And here is our HCl Lewis structure. So what's going to happen? What's going on here? Hold on, let me plug this in. My head's going to die. There we go. All right, so the lone pairs on this water are going to attack the hydrogen on that HCl. And that means this bond is going to be broken, and those two electrons are going to be deposited on the chlorine atom. And so what I'm going to be left with is this. The water is going to become hydronium, which is H3O plus 1. I'm going to be left with chlorine, who now has a full octet because we gave it those two electrons in that bond, minus 1. And so did I make hydronium in solution? Yeah, absolutely. So is hydrochloric acid an Arrhenius acid? Yes, the answer would be yes. And what we're looking at in these two pictures is that process right there that we've diagrammed out. We might also write it like this, H2O plus HCl yields H3O plus in solution. All right, so aqueous, and Cl minus aqueous. Right? That's how we might write that. So that's an Arrhenius acid. Any acid that produces H3O plus is classified as an Arrhenius acid. Now let's step out a little bit. Let's look at Bronsted-Lowry's theory. So the Bronsted-Lowry theory goes a step farther. It says that in order to be an acid, you just have to be able to donate a proton. You don't have to form hydronium. You don't have to make H3O plus. So there's a very narrow number of chemicals that make H3O plus. There are a lot more chemicals that can donate a proton, right? They have a hydrogen to give. And when we say donate a proton, we're talking about a hydrogen ion, right? Because remember, hydrogen has one proton in the nucleus, and it has one electron in the 1s orbital. So if I take that electron away, then I'm left with just the nucleus, which is just one proton. And so when we say donate a proton, what we're saying is a hydrogen is able to move from compound 1 to compound 2. Now, all Arrhenius acids are Bronsted-Lowry acids, but not all Bronsted-Lowry acids are Arrhenius acids. So in water, a Bronsted-Lowry acid is going to do the exact same thing that Arrhenius acids do. They're going to make hydronium. But the designation of whether it's an acid or base is going to depend on the reaction that you're doing, because some reactions don't have water present, but you still have an acid at work. Now, according to Bronsted-Lowry, the bases are those compounds that accept protons. And that makes sense, right? A base is opposite of an acid. Now, again, all of the Bronsted-Lowry bases are Arrhenius bases. So, or no, I'm sorry, take that back. All Arrhenius bases are Bronsted-Lowry bases. It works up. And so let's look at this example right here. We don't have any water present, but we have HCl and NH3. And we can see that this hydrogen is going from HCl over to ammonia. And the ammonia is accepting a hydrogen, right? It's becoming NH4. So that's NH3 plus an H. And so if we're accepting a hydrogen, right, because we became NH4, accepting a hydrogen, that makes us a base. So here is my base. HCl is donating the hydrogen, so that is my acid. Now, consequently, you've actually seen this reaction before when we were looking at the gas law notes, and we talked about Graham's law, and I showed you the picture of the two open containers, and there was that white smoke above one. We talked about like the rate at which the gases were diffusing in the air, effusing through a hole. That was the NH4Cl smoke that you saw. That was the solid. Now, interestingly enough, this compound is what we call a complex ligand, and I'll write that for you. It's a superstructure. So this would be a complex ligand. Ligand with a D. And what we have is an ammonium polyatomic ion that is coordinated or connected to a lattice of chlorine atoms. So that's a pretty interesting compound. Now, what about the other things that are in our formulas with acids and bases? What do we call them? Well, they are the conjugate acids and the conjugate bases. So let's talk about how we identify those. In this case, we've already looked at this formula. We know that, or this equation, we know that HCl is our acid because it's going to donate a proton to the water. All right, that's what it's going to do. The thing that is left over after proton donation is called the conjugate base of the acid. So here's my acid. This is what's left over, right? It's missing the hydrogen. It's missing one hydrogen. So it is the conjugate base. Now in this reaction, water is acting as a base. It's not acting as a Bronsted-Lowry base, as an Arrhenius base. It's acting as a Bronsted-Lowry base because it's accepting a proton. That means that H3O plus is the conjugate acid of water. So how am I tracking this? Well, the acid forms the conjugate base by losing a proton. The base forms the conjugate acid by accepting a proton. And it's pretty simple to track that. when you look for the easiest way to start is always to look for the conjugate base. So the conjugates are always going to be on the product side, and they're going to be whatever is left over when the acid donates its proton away. That's the definition. Now, conjugates always differ by one hydrogen, okay? And the definition is simple. Given that two species differ by one hydrogen, the acid has the extra proton, and the base is going to have one fewer protons, the conjugate base there. So H2O and H3O plus are conjugates because there's only one hydrogen as a difference between the two. H2O and OH minus are conjugates, right? Hydroxide and water, because water is the acid here. It has one more proton, and hydroxide is the base. It has one less proton. If something differs by more than one hydrogen, they can't be conjugates. So H3O plus, right, our hydronium, and hydroxide, they differ by two hydrogens, so they'll never be conjugates of each other. Now let's practice some of these. I'm going to give you the acid. You give me the conjugate base. So we know that the conjugate base is missing a hydrogen, and we know that when we take a hydrogen away, hydrogen has a +1 charge, so we lose a positive charge. So the conjugate base would be HS minus 1. H2S is neutral. Take away a H, take away 1, HS minus 1 charge. HCO3 minus, well, if we remove the H, we add a negative, CO3 minus 2. All right, that would be our conjugate base. How about water? If we remove a hydrogen and we add a negative charge, we go from H2O to OH minus. That's hydroxide. How about NH3? Well, we take away a hydrogen, we add a negative charge, NH2 minus 1. You try this one, HS minus. Take a minute, take an H away, add a negative charge. What do we get? Well, S minus 2. Now, something that's interesting about HS minus is that it's amphoteric. And amphoteric means it can act as an acid or a base. And that's simple, right? Now we know to act as an acid means to donate a proton. To act as a base means to accept a proton. And so HS minus could give up an H. That would make it an acid. It could also accept an H. That would make it act as a base. Let's go the other way. Let's start with the base, and you tell me the conjugate acid. So with the acids, we took away an H and we added a negative. So with the bases, we're going to add an H and add a positive. So H2O becomes H3O plus. OH minus becomes, well, H1 plus 1 is H2. Negative 1 plus 1 is 0, so just H2O. HPO4 minus 2, you do this one. Add an H, add a positive. Pretty simple. H2PO4 would be the conjugate acid. In H3, conjugate acid of this base, well, to be a base, you have to accept a proton, and that means you're accepting a positive charge. So NH4 plus 1. This is ammonium. HS minus, all right, we just looked at this one. We know it's amphoteric, so now it's acting as a base, which means it's going to accept a proton. So add a proton, add a +1, H2S. Now again, there are a lot of amphoteric molecules. Water is amphoteric. We've seen it on the acid side and on the base side. So let's talk about amphotericity, or the amphoteric nature of water. It comes from amphiprotic, all right? That is the word it comes from, in that the proton can move, like amphibious means both on land and in water. Amphi means both. It can go both, okay? It can be given or it can be accepted. Now, water is really important because we're mostly water. And the reason for that is because water can act as both an acid as a base and a base, so it makes a great medium to base life on. This allows water to do what's called autoionization, which means it can react with itself to form an ion. And this actually explains a lot of the reason behind why water is the universal solvent. So we have two water molecules here, and this first water molecule, right there, water molecule number 1, is attacking the H on water molecule number 2, and it removes it, and it leaves us with hydroxide and hydronium. So since water makes hydronium in solution, we can say that water is an Arrhenius acid. And since it makes hydroxide in solution, we can say it is an Arrhenius base. And if something can act as both an acid and a base, then we call it amphoteric. Now, there's a lot of different compounds that can be amphoteric. We find most of them around the semimetals. And here's a great example of one. Here is aluminum oxide. So in this first reaction, aluminum oxide is acting as the base, all right? And it's reacting with hydrochloric acid. In the second reaction, it's reacting with a base, so it's acting as an acid here to form a salt and water. And so in this case, right, even though we're talking about something completely different than water, we have aluminum, right, or aluminum oxide rather, which is acting amphoterically. Now, all of our oxides, or all of our amphoteric compounds here in the middle, are going to be an oxide. They're bonded to oxygen, so that's what we're talking about here. So any of the ones there in purple are capable of being amphoteric if they're bound to oxygen. Now let's talk about strength of acids and the strength of bases, because, one of the things people come into chemistry with this great false expectation about is like, oh, there are these acids that'll like just melt away the universe, right? They're so strong. Well, acids can do some pretty crazy things to organic tissue. They certainly don't melt it, but they can dissolve it. And we need a way to categorize how strong an acid is compared to another acid. And so we use something called pKa. And pKa is the point where the pH, or is the pH rather, where the ions in the solution are at equilibrium. So we're not getting any more ionization of the acid. Now, the lower the pKa, the stronger the acid is. That's really important, okay? And if you have a compound, or you have a solution rather, and the pH of that solution is lower than the pKa of the acid you're going to put into it, then the compound is going to be protonated by the acid. The acid is going to do work on that compound. So here's a chart of your pKa's. And up at the top, we have the strongest acids, and I had to cut it to make it visible on the slide, so it just kind of picks up here. And we can see the pKa's of these acids. The pKa's go down the middle column. And so we can see that the strongest acid on this chart is the pKa of -9 for sulfuric acid. And something that's interesting is the stronger the acid, the weaker the conjugate base that it makes. So although sulfuric acid is the strongest acid on this chart, it makes the weakest conjugate base on that chart. And you might be saying like, okay, well, what do you mean makes the weakest base? Well, remember, when you put H2SO4 into water, we're going to make H3O plus, and we're going to make this HSO4, right? And because we're losing a hydrogen, the conjugate base, there we go, we have a minus. So this is my acid. Here is my conjugate. Oh, we'll go back. What happened? There we go. Conjugate base. Here is my Bronsted Lowry base. Here is my conjugate acid. So the stronger the acid, the weaker the base, right? And that's how that goes. So the pKa lets us compare acids to acids. If you have a negative pKa, you're likely a very strong acid. If you have a positive pKa, you're a very weak acid. So like ethane, which is C2H6, that is an extraordinarily weak acid. All right, it has a pKa of 50. All right, that's not a very strong acid at all. Water has a pKa of 15.7. All right, so not a very strong acid. And also, when we compare pKa's, and we talked about it a minute ago, if the pH of your solution is, let's go back. If the pH of your solution is lower than the pKa, the compound will be protonated. Right? That means if the pH is higher than the pKa, then the compound won't be protonated. Right? That's what we would say there. So if I have water, right, which has a pH of 7, and I add H2SO4, which has a pKa of -9, well, 7 is greater than -9. And so that tells me this hydrogen is going to protonate that water. So that's how I'm going to end up with I don't know why I did an equal sign there, the H3O plus and the HSO4 minus. So that's what the pKa tells me. It tells me when something's going to be protonated or if it's not going to be protonated at all. Now, when we're talking about protonation, we have to talk about monoprotic versus polyprotic. A monoprotic acid, so one proton, can only donate one hydrogen ion per molecule. It has one ionization step. So all of our binary acids that only have one hydrogen, or our oxyacids that only have one hydrogen, they are monoprotic acids. Now, a polyprotic acid is an acid that has more than one hydrogen to give away, and it has to give them away in steps. So first you give the first one, and then maybe you give the second one. So sulfuric acid is a great example of this. Phosphoric acid is a great example of this because they have more than one hydrogen to give. So we can kind of look at that in our in a visual here. We can see that HCl only can form one. It can only give one hydrogen away. But H2SO4, because it has those two, sulfuric acid, can do a first step to make hydronium. And then it can react with any water that's left over in a second step to make more hydronium and leave you with sulfate in solution. So that would be the difference in a monoprotic and a polyprotic acid. And this is, again, we're still in the Bronsted-Lowry family of acids and bases. So let's do the last one. Let's finish up. Let's look at Lewis theory. Now, I'm not going to spend a lot of time on Lewis theory because Lewis theory is really the most broad definition of an acid or base. And in all honesty, Lewis theory tells us that everything is an acid or a base. Because in a Lewis theory, acids accept electrons and bases donate electrons. Easy way to remember this: A for accept, A for acids for the Lewis theory. Now, in this definition, just a proton floating around is an acid, all right? And if you are just talking about electrons moving, you don't even need a hydrogen in order to get an acid. So silver, in this example we have down here, is acting as a Lewis acid because it is accepting electron pairs, right? These two pairs, there's two of them, right? Because we have two. So we'll draw the other one. It is accepting, right, electron pairs to form this new compound, right? Here are the electron pairs that it accepted. Electron pairs, right? Because we know that a bond is formed by a pair of electrons. Now, according to Lewis theory, silver by itself is just an acid. Now, you use Lewis theory in organic chemistry a tremendous amount. We're not in organic chemistry, right? We're in inorganic chemistry. So I want you to know it's out there. I want you to look at it, but we're not really going to go into any great depth. So let's sum it up. Arrhenius definition is the most specific. The Lewis definition is the broadest description of an acid or base, and Bronsted-Lowry is kind of in the middle. For Arrhenius acids, they have to produce H3O plus in solution. The base has to produce OH minus in solution. All right. For Bronsted-Lowry, you have to donate a hydrogen to be an acid, or you have to accept a hydrogen to be a base. For Lewis acids, you just accept electrons. For Lewis bases, you donate electrons. And we can kind of look at it like this. There's a very small group of Arrhenius acids. All Arrhenius acids and all Arrhenius bases are included in the definition of Bronsted acids and Bronsted bases, right? Or Bronsted-Lowry acids and Bronsted-Lowry bases. Both of those are included in the definition of the Lewis acid or the Lewis base. Okay? So that's our introduction to acids and bases. In the second video, we're going to be looking at the behavior as far as acids and bases as electrolytes in solution. We'll look at some practice problems. We'll look at anhydrides, and we'll go a little bit deeper. All right, but for now, that's the end of the first video. If you have questions on this, let me know. I'll be glad to help explain it to you.